Okay, now in regards to the exam coming up on Monday, we'll finish up the mole, I think, probably Wednesday or Thursday. Okay, I'm hoping it's Wednesday, so we'll have a full class to do a unit exam review. All right, and in the unit exam review, essentially I will go over the important concepts that we covered in the unit. All right, I will talk about how those will be tested on the exam, all right, whether they be multiple choice, written response, or both. And I might even give you a little bit more detail on as to how I will ask about certain things. And then I will give you a review package, okay, that has old exam questions that I don't use anymore, you know, things like that, just practice stuff that you can work on over the weekend. All right. You should probably, though, like in the next couple of days, start your exam preparation. Okay, you will not do an effective job of exam preparation if you leave it till Sunday night. There's simply too much stuff for you to go over and practice and review for you to do it effectively in a one-night cram session. Okay, so if you spread it out over the course of the week and you do 5 or 10 minutes here and there, then you can still do kind of a big session on Sunday. Obviously, that's still effective, but if it's the only thing you do, it won't be as effective as you would like it to be. Right, so I would say over the next few days, start looking at things, you know, and say, oh, I didn't really get that. Look at your quiz marks and go, oh, I didn't do very good on that quiz. Maybe I should come in and see Mr. Codera about that stuff and get a little bit of help on it. Okay, things like that. But if you're doing that now, you'll have the chance to ask for help and figure things out. If you leave it till Sunday night, what can you do then? Stress, not get any sleep, and not do well on the exam on that part of it on Monday. Okay? Because if you email me on Sunday night and go, Mr. Codera, I really don't get how to do this, I'm going to go, how am I supposed to help you over email? Okay, like there's really not much I can do for you at that point. But if you come in during the week and scheduled help, absolutely, there's all kinds of things that I can do to help you then. All right? But it involves you being kind of prepared ahead of time. Okay? So, things to think about. All right, so the last thing that we're going over in this unit is the mole. Okay, and the mole is a measured quantity. All right, it's not the little rodent. Okay, nor is it a growth. Okay, the mole is, okay, a measured quantity, and it refers to a specific number of atoms or molecules or particles of a material. So if I say I have a mole of oxygen, I have a certain number of oxygen molecules. All right. If I say I have 1 mole of iron, I have that many atoms of iron, of the same number of atoms. All right. Does it mean I have the same amount, like let's say mass of both? No, not necessarily, because iron atoms are much heavier than oxygen atoms are. All right. In fact, an iron atom is heavier than a molecule of oxygen is. All right. So if I have 1 mole of iron atoms and 1 mole of oxygen molecules, the iron is going to be more massive just because the atoms are bigger. Everybody follow me there? Okay. So the discovery, or not so much discovery, but the invention or the idea of the mole was really important in terms of being able to sort of prove what went on in a chemical reaction, because it allowed people to figure out and actually even predict how much product they were going to get from their starting materials. Okay, and I don't mean if I have 10 grams of starting materials, they could predict they would have 10 grams of products. Obviously, they knew that. That's the law of conservation of mass. But if they had a reaction and they were going to get 5 different products, they could predict the amount of grams of each. All right. Now that's pretty useful, especially in terms of like industrial processes. If you are producing, let's say, ammonia for use in fertilizer, you want to be able to produce, you know, be the most efficient that you can and not have stuff left over. So if you know you need to produce 3 tons of ammonia for fertilizer, you need to know exactly how much of each of the starting materials you need to have. You don't want to have extra because that'll be wasteful. Everybody follow me there? Okay, so it was kind of important in that regard. So we need to understand that the mole is a unit for measuring the number of particles. Okay, so it talks about number of particles. We will relate it to mass. We will relate it to molar mass, which is like essentially the mass of 1 atom. Okay, things like that. We're going to look at the relationship between moles mass and molar mass. And lastly, use the Molar equation to solve problems. All right, so there is a little bit of math involved in using the mole. But the mole equation is really, really easy. This is it. N equals little m over big M. All right, there's only 3 variables in that formula. Now, before you get any ideas, these are not allowed in high school. Because I know a bunch of you are thinking, if only 3 variable formula, I can use a triangle. No, you can't! Triangles are for the weak. Okay? You can do algebra. You don't need a crutch, because I'm cruel. Okay? And I will kick that crutch out from under you and make you fall down, because you need to be able to do algebra. It is very important. Okay? Because while this triangle will work for this formula, and maybe 1 or 2 other formulas that we might use in this course, it will not work for this one. Which you will use in this course. Okay? And it will certainly not work with, oh, let's say something like this. I challenge you to find a triangle that will work for that. Okay? So if all you've done all the way along is, ooh, triangle, 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 you're screwed when you get to this. Because you don't know how to do algebra. You just know how to draw pretty triangles that are useless. Okay? So, this is a no triangle zone in here. I see a triangle on your sheet, I will hunt you down. Okay? Question? No? Okay, yeah, N equals M over M. This is the mole equation here. All right? This shows you the lack of creativity of chemists. There are 26 letters in the English language. They chose to use the same letter twice in a 3-variable formula. Okay, so I'll go over what each one of those things means when we get to the actual formula, but we'll talk about the mole here first, now that I'm done my triangle rant. Okay, I teach physics, so I can't stand to see triangles because I just see how they fail people immediately. All right, so the mole concept. We can express the amount of something using mass. Okay, we can use grams. All right, but sometimes we want to be even more precise than grams. We want to say there's exactly this many particles of a material. And when we have that, okay, we deal with moles. Here's why we deal with moles. How small is an atom? Really, really small. All right, to give you an idea, in 1 mole, there are this many particles. Okay, it doesn't matter what you have. If I have oxygen, there's that many molecules of oxygen in 1 mole. If I have hydrogen, there's that many molecules of hydrogen. If I have sodium, it's that many atoms of sodium. All right? That's why we use the word particles here. It depends what we're dealing with. If we're dealing with an element, it could be atoms. If we're dealing with a compound, then the smallest unit for that is a molecule. You guys follow me there? Yes? All right? And if I have water, okay, if I have a mole of water, I have this many molecules of water. All right? For every material, it's the same number of particles. It doesn't mean it'll be the same volume or mass or anything like that. Okay? Because everything's molecules or atoms are different sizes. Okay? So when we're dealing with even small amounts of things, okay, the number of particles very quickly becomes overwhelmingly large. All right? So we use the mole to represent very large numbers of particles. All right. Now, to give you some ideas, like 6.02 times 10 to the 23 is 602 with 21 zeros behind it. I'm not like I would go all the way across the screen writing that number out. All right. It's huge. It's mind-boggling, that number. All right. And that's just, okay, for 1 mole. 1 mole isn't very much. If we're talking about 1 mole of hydrogen, you know what the mass of this many particles of hydrogen is? 1 gram. 1 gram of hydrogen is an incredibly small amount of stuff. Okay, so we're talking about very, very small amounts here. All right, so it's convenient if we're talking about number of particles to have a number that represents them. All right, in the same way as we use a dozen to represent how many? 12, right? It's easier to say I've got, 2 dozen rather than I have 24 of something, okay? Or I have 4 dozen rather than I have 48, and so on. Okay, so it works in kind of the same way. It represents a certain number of something. In this case, it represents 6.02 times 10 to the 23 particles of whatever it is you're dealing with. All right. All right. Now, the guy who came up with this idea, his name was Avogadro. And this is his number. That's what we refer to it as. That's Avogadro's number, 6.02 times 10 to the 23. Okay. Now, when I show you the picture of Avogadro, you'll know why he called his unit the mole. And it's not because he has a big mole on his face, but he looks like the little rodent. It's really like, how people look like their pets? Yeah, well, this guy looks like a mole. Okay. Now, the idea here, the way he came up with this is he said, we have to have some way to represent large numbers of particles. So I'm going to kind of find a number that makes sense. Now, you may look at that number and go, how did that number make sense to anybody? But here's why it made sense. He said, I'm going to start out with the simplest material there is. What's the simplest material? Hydrogen. He said, and I'm going to take a gram of hydrogen, and then from what I know about, the mass of protons and electrons, I'm going to figure out how many atoms there are in 1 gram of hydrogen. And then we're going to use that number as a kind of standard unit of measurement for all materials. And then I'll be able to figure out what 1 mole of everything has a mass of. Okay? And that's exactly what he did. Now, of course, at the time, their estimates of the mass of a proton, mass of an electron weren't quite right. Which is why now when we look at the molar mass of hydrogen, it's actually 1.00794. All right, he was pretty close. All right, but okay, that's where we get that number from. A gram of hydrogen had this many atoms in it. All right, everybody follow me there? Okay. All right, moving right on then. All right, so the mass of 1 mole of a substance is known as that substance's molar mass. Molar mass is the capital M in the formula N equals little m over big M. All right, so all the masses that are on your periodic table, okay, the ones we call the atomic masses, are just that. They are the mass of that many atoms of that material. Okay? So if I have 6.02 times 10 to the 23 atoms of hydrogen, it'll have a mass of 1.00794 grams. If I have 6.02 times 10 to the 23 atoms of magnesium, that'll have a mass of 24.31 grams. Okay? Everybody follow me there? So these, we call them atomic masses, but they're actually the molar mass, the mass of 1 mole of each of these elements. John, question? It's a weighted average of all the isotopes, yes. Yeah. Okay. It's still accurate enough for what we need to do because it represents, again, the weighted average of all the different isotopes, right? Okay, so hydrogen, like we said, 1.01 grams per mole. Okay, that's the molar mass. The grams, the mass of 1 mole. That's where we get those units from. Grams per mole, the amount of mass of 1 mole. Okay, so for compounds, the molar mass is calculated by adding the atomic or molar masses of all the elements together. All right, so if we're doing water, for example, all right, and the example is written out here, but we'll show it to you here. All right, water is H2O. So if I want to find the mass of 6.02 times 10 to the 23 molecules of water, I take the molar mass of hydrogen, 1.01, and how many hydrogens are there? 2. Multiply that by 2, and add it to the molar mass of oxygen. All right, and so that's going to give me 18.02 grams per mole. Okay, so if I have 6.02 times 10 to the 23 molecules of water, it'll have a mass of 18.02 grams. It'll have a volume of 18.02 milliliters, just because water's density happens to be 1. Okay, so how much water is that? Not very much. Okay, 18 milliliters is what? 2 teaspoons approximately? 2 tablespoons, sorry, approximately. All right, it's not very much. Okay, it isn't very much. Or 1 tablespoon is 15 milliliters. Is that what it is? Okay, something like that. I can never remember. No, we're not going to be dealing with much volume. Just to give you an idea of how much, because when I say this many grams, people go, "Yeah, I don't know grams, right?" No, like how many of you, if I asked you what your mass is in kilograms, would actually know? Yeah, well, like not many, right? Most of you know it in pounds, because we're not completely converted yet. All right, so that's how you would calculate it. You take the molar masses of everything that's in the compound and multiply them if you have to. If they have subscript numbers, we multiply by that number, right? And then add them up. Right? It's not a difficult procedure by any stretch. Okay. All right. That's Avogadro, by the way. Kind of funny looking. All right, I'm going to put a couple of compounds up here. I want you guys to calculate the molar masses of them. Okay, start out simple. Okay, give you a couple minutes to try those. All right, let's just have a look at the first couple here, just to make sure we're all on the same page here. So if we're going to find the molar mass of NaCl, we're going to have 22.99 plus 35.45, right? Okay. Okay, and then 58.44, right? And don't forget units, grams per mole. All right. Unfortunately, guys, an answer with no units is considered wrong. Okay, because I don't know whether it's apples, oranges, old ladies and walkers. Okay, you have to have units on it, otherwise I don't know what it means. Right. Now for magnesium phosphide, we're going to have 24.31 times 3 plus, for phosphorus, 30.97 times 2. So whoop, don't forget the multiplication. All right, so we're looking at 134.87 grams per mole. Okay, we getting these right, guys? Right, it's not rocket science, right? All right, for iron 3 oxide, you've got 55.85 times 2. Okay, plus 3 times 16. All right, so 159.7 grams per mole. How many people have done all of them? Okay, I'll give you a couple minutes here just to finish up the rest, and then we'll go through them. All right, so that's what usually happens. The first time I put a polyatomic ion up here, people kind of go, oh, well, but polyatomic ions aren't on the periodic table. How am I supposed to know their masses? Are they made up of elements whose masses you know? Yeah, so it's the same as figuring this out. You just do it element by element. All right, so for this one here, I have 1 copper, and that's what, 58.93. No, that's cobalt. 63 point what? 55? 63.55 plus 1 sulfur, 32.06. 07. Okay, and then 4 oxygens, so 16 times 4. Right? You have to do molar mass element by element. All right? Doesn't matter what the compound looks like, it's got to be done element by element. All right, so we plug all that together here, 63.55 plus 32.07 plus 16 times 4. All right, we got 159.62 for that one. Grams per mole. Okay, so the same goes for these last two. How many people have done the last two? Okay, so let's just go through those. So we got potassium permanganate here. So with potassium, we've got 39.10 grams per mole plus manganese, which is 54.94 plus 4 oxygens. Okay, so 158.04. Grams per mole. Okay, so this is why when we were talking about compounds and figuring out how to, when we were balancing, you had to be able to interpret how many oxygens this is. Is that kind of important now? Yeah, because you need to know what number to multiply oxygen by when you're calculating the molar mass. So there's 1 calcium here, and that's 40.08, right? Yeah. Okay, 40.08 plus, how many nitrogens? 2, so 14.01 times 2, and 6 oxygens. So 40.08 plus 28.02 plus 6 times 16 is 164.1. Okay, now just so you're aware. Okay, just so you're aware, on an exam or quiz on the mole equation, this is what I would do. I would write out the name of the compound in words. Why am I going to do that? Yeah, to see if you still know how to swap and drop. Okay, if you don't do that correctly, are you going to get the molar mass right? No. Right? So it is really important that we can drop and swap correctly. All right? I'll tell you this. Last year on the unit exam, I put magnesium chloride, I'm pretty sure it was, as one of the molar mass or mole equation questions on the unit exam. And it was like, calculate the mass of this many moles of magnesium chloride. And it wasn't that people couldn't do the math, but they went like this. The rest of the math was fine, except that they had the wrong molar mass for magnesium chloride because they forgot to drop and swap and get the right formula for magnesium chloride. Okay, so really important. Okay, if you were thinking I'm really good at doing all the drop and swap and everything like that, so I don't need to study it, take a couple minutes. Okay, because not only will it affect you in the reactions part, as you've seen on your assignment, but it'll get you here too. Right? That's why the fundamentals of anything are so important to master, right? Okay, questions on how those work? Good. All right, so when you're interpreting a chemical equation, we've got these coefficients in that we put in. Right, Brooklyn? Okay? And they are used to balance the equation, make sure that we got the same number of everything on both sides. Up to this point, we've said that that means there are 3 molecules of hydrogen gas and 1 molecule of nitrogen gas, making 2 molecules of nitrogen gas, or of ammonia. Does it have to mean molecules? It doesn't. It can mean moles too. It's a ratio. Okay? If I'm talking 3 molecules, 2 molecules, and 1 molecule, if I'm talking moles, I can use the same numbers. It's all about how many there are compared to the others. There has to be 3 times as much hydrogen as there is nitrogen. Okay? At least from a molecular or a molar point of view. Everybody follow me there? Now, from a mass point of view, much different, because hydrogen is lighter, way lighter. All right, but I know that at least molecule to molecule or mole to mole, I got to figure out that I always have to have 3 times as much. All right. Now, if I know that this hydrogen gas here is 2.02, and I know that this nitrogen gas here is 28.02, how did I figure that out? John? Right. The atomic mass on the periodic table deals with 1 atom. All right. This has 2. So I take the 14.01, multiply it by 2. All right. So there's 28.02, there's 2.02, and I need 3 times as much of this as I do this. All right. So if I wanted to just make this reaction happen, all right, I would need 28.02 grams of nitrogen, and I would need 6 grams of hydrogen. Everybody follow me there? How much ammonia is that going to make? Yeah, 34.08 grams. How did we figure that out? Yeah, we added it. Law of conservation of mass says whatever I start with, I have to finish with. I can't have more mass on the other side, can I? Right? And that's where you're going to go into Chem 20 and figure out, they'll give you a question that says, you have this many grams of hydrogen. How many grams of product will you have if you have as much nitrogen as you want? All right? Will all the nitrogen react? No, it'll react until it runs out of hydrogen to react with. Okay? The rest of the nitrogen will just sit around. Okay? The reaction can only go until one of the things is used up, and you'd be able to figure out how much of this you would get. All right? That's where you're going in Chem 20. We don't do any of that in Science 10. We used to, okay? But we don't anymore. Okay. So that's all this is saying here, looking at it from different standpoints. It could be 1 molecule, 3 molecules, okay, making 2 molecules. It could be 10 molecules, 30 molecules, making 20 molecules. Is it still 1, 3, 2? Yes. Okay. It could be 1 mole, 3 moles, making 2 moles. All right. Or it could be, like we said, 28 grams of nitrogen, okay, times 6 grams of hydrogen, making 34 grams of products. 34 grams of reactants, 34 grams of products. Okay. All right. So like we said, particles is one way to look at it. Okay, mass, whatever. That's Avogadro. Look at his eyes. He looks kind of like a mole. You ever seen a mole? They got like really big eyes. Yeah. So that's him. How many people have seen Austin Powers? Yeah, I'm a big Austin Powers fan. Oh, come on. Come on now. Don't be like that. 2 can play that game. Oh, it's not in there. Where else would it be? Okay. Yeah, I could. Okay, so let's skip right past because we've already talked about that. All right, the mole equation. So here it is. Okay, N equals little m divided by big M. N stands for the number of moles. All right, so you're calculating number of moles if you're calculating N. Little m is the mass of the material in grams. Okay, and m, big M, is the molar mass. Okay, and you can always get that from your periodic table. So you will always have molar mass as long as they tell you what the material is. Quick algebra review. You'll see why I did them all in different colors in a minute. I want to calculate mass. How do I get little m by itself? Right, multiply both sides by molar mass. Okay, manipulate the equation, right? If I want to move something, I always do the opposite of whatever is currently being done. All right, right now I'm dividing by big M. If I want to get little m by itself, to move big M, I have to multiply both sides by big M, which is essentially doing this. All right, algebraically, it looks more like this, right? Multiply both sides by M. Okay, and what's M over M? 1, right? Okay, so it cancels off. Anytime you have the same variable over itself, it cancels itself off because it comes out to 1. Everybody follow me there? All right, so that's kind of what we did there. All right, so that's one of the manipulations you might have to do. In fact, it's essentially the only manipulation you are going to have to do. This equation is already set up to give you the number of moles. Okay, it's already set up to give you the number of moles, and you're always going to have big M, aren't you? Okay, you're always going to have big M because you always have a periodic table and you can always calculate it. You'll never use the mole equation to calculate big M. All right, simply because you never need to. So the only manipulation you'll ever have to do is that one. Can we handle that? We don't need a triangle for that, do we? No triangles. Okay. All right. Now, another thing that you may be asked to calculate after using the mole equation, or even before sometimes. What if I ask you not for the number of moles, but I ask you for the number of particles? How would I get that? Jason? Nope, because if I divide m by, I don't know what that'll give me, but it won't give me that. Do I know how many particles there are in 1 mole? Okay, 6.02 times 10 to the 23. So if I've calculated n, can I calculate the number of particles? Right, okay. If we multiply the number of moles by 6.02 times 10 to the 23 by Avogadro's number, we'll have the number of particles. All right, so if I have 2 moles, it's 2 times 6.02 times 10 to the 23, and that'll be my number of particles. Okay, everybody follow there? Right. The other thing that could happen is I could give you a question that has the number of particles in it and ask you to calculate the mass. Okay, so if you know the number of particles, can you calculate the number of moles from that number? So instead of multiplying, you would divide by Avogadro's number, right? And that would give you the number of moles. So, okay, there's kind of this secondary equation that you're not really going to write down or have ever, but okay, the number of particles equals n times Avogadro's number, 6.02 times 10 to the 23. Right, and then obviously you can manipulate that around. If you needed to get n, you would divide the number of particles by 6.02 times 10 to the 23. Okay, but you'll be using both a fair amount. Now, question that always comes up, Mr. Coder, how do I put that number into my calculator? All right, the answer is this. You will have to use your EXP button. All right, or if you have a TI 83, 85, 80, whatever. Okay, I don't know what they're up to now. They're probably up in the 90s now. All right, but what you do on that, and now I have to shut this off and turn it on again. All right. So here's what you do. If I want to say figure out how many particles there are in 2 moles, I would go 2 times and then in brackets, okay, 6.02. Then you hit your second function and the comma button. It has 2 E's above it. On many calculators, putting something into exponents means using the EE button. You may actually have an EE button if you don't have a TI. All right. E, and then you just put 23. The E means times 10 to the power of. Everybody follow me there? Yeah? And then enclose that in brackets. That number always has to be enclosed in its own set of brackets. If you don't, your calculator defaults to do order of operations, which means if I go 6.02 E23, don't put a bracket here and then put something after it, it assumes whatever I put after it is part of what? Yeah, part of the exponent, part of the 23. All right, and then you get really weird numbers. All right, so that's how you enter it on a TI-83. If you have something else, look for either an EE button or an EXP button. Okay, I think if you're using your phone, which by the way you can't do on the exam, all right, look for an EXP button on there. All right, and that will put it into scientific notation for you. All right, so guys, just so you are aware, when you write the unit exam on Monday, so that's a week from today, you must have a calculator. All right, you may not use your phone, iPod, anything else that is Wi-Fi connectable, right, as a calculator on a unit exam. All right, so you do need to have a scientific calculator for Monday. All right, you don't have to have a TI-83. Right? You can go to the dollar store and buy the cheap, junky, okay, scientific calculator. Okay, go to Wally World. That's Walmart, by the way. Okay, you can get cheap, crappy, all right, you know, $5 scientific calculators. They don't have to be a graphing calculator. All right, and then if I do that, obviously, then I'll get a number that has an exponent in it. Okay, 1.02, or sorry, 1.204 E24. Right? How do you write that? When you're giving me the answer, you write that as 1.02 times 10 to the 24. Okay. The thing I see people do most often when they're punching into their calculator that inevitably really messes them up is this. Okay, they go 6.02 times 10, okay, and then they go E. Did you just give it an extra power of 10 by doing that? You did. Okay. Now when you go E23, it's not going to like you very much. Okay. So yeah, don't do that. All right. It's just messy. So just E23 and it'll put it in for you. That's all you need. Just make sure it stays in brackets, right, so that it works. All right. Something really wonky with that calculator. All right, so we did a whole bunch of that stuff already. Let's maybe try these ones again here, just molar mass stuff before I go on to the thing I'm going to cover here near the end. Oh, did I? No, I was supposed to put 1.2. Yeah, no. Okay, guys, sorry. This should have been 1.2. I had 6.02 in my mind here. 1.204, right? Okay, times 10 to the 24, sorry. I had a brain fart there. All right. You know what? We've already done that. Let's just move on to, okay, doing these. So here's what I'm going to do. There's only 4 ways I can ask you a mole equation question. All right? There's only 4 ways I can, you know, like mess up this question, move it around, whatever, for you to calculate. Only 4. So what I'm going to do right now is show you all 4 examples. All right, is that going to be valuable? Yes. Should you watch this podcast later? Yes. Okay, just make sure you have a look at that. There's only 4 ways I can ask you about a mole equation question. All right, this is the easiest. How many moles of calcium chloride are in 90 grams? All right, whenever you're solving a problem in science, the first thing you write down are your givens. That is, the variables, values that the question gave you, because it's worth a mark. All right, so how many moles? That means I'm looking for N. Okay, it tells me CaCl2, so I can calculate molar mass. All right, I can use my periodic table for that. So I'm going to have 40.08 plus 2 times 35.45. So 40.08 times, whoa. All right, so our molar mass is 110.98 grams per mole. All right, and they give me 90 grams, which would be which variable? Little m, mass. Okay, you do this, 1 mark. All right. Now, the mole equation is N equals little m over big M. Is that set up already for this question? Yes, because I'm asked to solve for N here, so it's already set up. All I have to do is plug in my numbers. 90 over 110.98. Okay, so in this case then, all right, 90 divided by my answer gives me 0.81 what? Moles. Right? And we abbreviate mole to MOL because we're very busy and we don't have time to write the whole word. Okay? That's why we have an abbreviation for at. We're too busy to write the whole word. Okay. All right. Does that make sense, everybody? Okay. So this would be probably like a 3-mark question. I'd give you 1 for your givens. I would give you 1 for showing your math. 1 for your final answer. Okay. Sorry. Anyone still need that? Can I move on to the next one? All right, so our second example. What's the mass of 4.5 moles of magnesium bromide? And this is exactly the way I would ask this on a test, because I would give it to you in words. Okay, so writing down our givens here, N equals 4.5 moles, one of my givens. All right, we're asked to find mass, so we don't have it, but we're told the material, magnesium bromide. And what I always do if I'm given it in words is I actually write the formula down. Okay, MgBr2. And then I figure out what my molar mass will be. So for magnesium, we got 24.31 plus 70.9 something. 79.9 over. All right, that'll give me my molar mass. (184.11 grams per mole). Okay, so 1 mark. Now I need to use the mole equation. N equals little m over big M. But now that equation is not set up for what I'm looking for. I'm looking for little m. So how do I get little m by itself? Right, multiply both sides by big M. Big M cancels there, and I've got this. All right, so m equals n times big M. We plug in that. Okay, we're going to have 184.11 times 4.5. Okay, so you would get a mark for your manipulation. Okay, you would get a mark for plugging in the numbers correctly, and a mark for your final answer. Okay, so 828.5. Right, what are my units going to be for this one? Grams. Okay, so that would be a 4-mark question. Okay. Questions on that one? All right. Those are the two easiest examples. The next two involve having to use Avogadro's number as well. So they have an extra step. It's not that they're any more difficult, they just have an extra step. All right. How many molecules are in 600 grams of silver nitrate? All right, so M equals 600 grams. Okay. I don't know N, but I do know that this stuff is silver nitrate, AgNO3. Okay, so that's what, 107, yeah, 0.87. Plus 14.01 plus 16 times 3 to get us our molar mass of silver nitrate. Right, 169.88 grams per mole. Okay. Now, even if at this point you're kind of lost, okay, and you're not sure how to get to particles, what can you calculate right now? Right, you can calculate the number of moles. At least go that far. All right, you're going to get a mark for your givens. Okay, but right now you have two parts of the mole equation, n equals little m over big M, which means the next step has to be calculate the number of moles. Right? Because if I know the number of moles, can I get the number of particles? Yes, by multiplying by Avogadro's number, right? Okay, so calculate the number of moles. We're going to have 600 over 169.88. All right, so we got 3.53 moles. In general, guys, we want to keep all of our decimals until the very end. Okay, I'm rounding off just because I don't want to write them all down, right? But I will keep them in the calculator. Generally, that's what we want to do. Keep all the decimals until the very end, and then you can round off, okay, to like 2 decimal places or something. Okay, so 3.53 moles. If I have 3.5 moles, 3.53 moles, and I want to know the number of particles, okay, remember that the number of particles, okay, can be calculated knowing Avogadro's number. N, number of moles, times the number of in 1 mole. Okay, and this is no different than, you know, if somebody said they had 3 dozen eggs. How would you figure out how many eggs that is? 3 times 12. This is no different. I have 3.53 moles, and this is how many there are in 1 mole. All right, so you multiply. Okay, so when we're multiplying that out, remember that this is what it looks like. So I take this number, okay, conveniently if you have a graphing calculator, you can just use the answer function, okay, times, in brackets, 6, decimal, 0.2, exponent 23. All right, so it tells me I have 2.13 times 10 to the 24 particles. Okay, now should I say particles or should I be more specific? Molecules. All right, so Mark's distribution for a question like this. Like we said, 1 for your givens. Okay, 1 for calculating the number of moles. 1 for calculating or showing the calculation involving Avogadro's number. And 1 for your final answer. So that would also be a 4-mark question. Questions on that one? Okay. All right, last one. I give you the number of particles in the question and ask you to calculate the mass. So what do you have to start with this time that we ended with last time? Avogadro's number. All right, we can always get to the number of moles if we know the number of particles, because Avogadro's number tells us how many atoms or particles there are in a mole. All right, so first thing I need to do then is calculate the number of moles, right? And that's going to be the number of particles divided by, this time, Avogadro's number, the number in 1 mole. Okay, so you would get a mark for that calculation. Okay, so we're looking at, when we punch that in, it looks like this. So in brackets, 1.54, okay, second E 25, end brackets, divided by Avogadro's number, also in brackets, 6.02, second E 23, right? And it ends up being 25.581 blah blah moles. Okay, so now I know how many moles I have. They tell me that the stuff I'm dealing with is diphosphorus tetraiodide, which means I can calculate molar mass. So that's P2, right, I4. Should I reduce that? No. Is it ionic? No. If I'm given prefixes, I don't reduce. The prefixes tell me these are the numbers. Don't mess around with them. Okay? If it's ionic and it's 2 and 4, then you reduce to 1 and 2. Right? For molecular, rules are different. All right, so now we've got 32.07. No, 30.97. Okay, plus iodine's heavy. 126.90. Okay, so now I've got the stuff for my molar mass here. So 2 times 30.97 plus 4 times 126.9. And we got 569.54. Grams per mole. Do I now have 2 parts of the mole equation? Yes, I have N and I have big M. So now I can go back to the mole equation. N equals little m over big M. I'm looking for the mass, which is little m. So I multiply both sides by big M. Okay, and I'm set up. You would get a mark for that as well. Okay, you get a mark for this kind of givens slash molar mass calculation. So we're up to 3 marks already. Okay, plugging in our numbers, we've got 569.54 times 25.58, the number of moles. All right, so times 25.58139535. All right, is that a lot? Well, it's 14.5 kilograms. Okay, but we'll write it down as 14,569.63. And our units are grams. Okay, again, always remember to put units on your answer. Okay, that's the only 4 ways I can ask you about the mole equation. There will be no surprises on the unit exam. I will ask all 4. All right, obviously with different materials, but okay, that's all I'm going to ask you. So if you practice those, okay, and practice the sort of fundamentals again. So the fundamentals are calculating molar mass, okay, remembering what Avogadro's number means, how many particles in 2 moles, 2 times Avogadro's number, okay, how many particles in 5.5 moles, 5 times Avogadro's number. Okay, remembering those fundamentals is important to doing a question like this quickly and efficiently. Okay. All right, questions on any of those? All right then. Now, I'm going to give you the mole concept worksheet now, okay? And you guys can get started on that. On number 1, does the material matter? Like, does it is there, if I had said there's 1 mole of hydrogen atoms, would it have made any difference? No. How many of anything is there in 1 mole? 6.02 times 10 to the 23. Doesn't matter what material it is. That's the beauty of the mole. It applies to everything. If I have 1 mole of water, I have 6.02 times 10 to the 23 molecules of water. Okay? If I have 1 mole of gold, I have 6.02 times 10 to the 23 molecules, or sorry, atoms of gold. All right? That's simple. The key for this is on my website. All right? So if you want to check your answers as you go, okay, same place as always. Okay, Science 10, Notes and Assignments. Okay, and we are looking at chemistry here, and you'll see keys to all mole equation worksheets. And it's right there. All right, so if you want to check your answers as you go, that's where you can check them. All right, don't do this tonight. Okay, we're going to be working on this tomorrow in class. Okay, Wednesday in class. We've got lots of time to work on this. I will be putting the quiz up later on today. It does not have any mole stuff on it. Okay, strictly predicting reactions tomorrow's quiz.